Hello, my name is Manabendra and I work in quantum cosmology. Today I'm going to talk about constraint analysis. Um, uh, in fact, it's not possible to cover the whole structure of constraint analysis in one session, but rather I will be discussing what we mean by constraints in a physical system, and it's important because in nature all the fundamental forces comes with some constraints. So meaning that apparently there are more. It seems that there are the number of actual degrees of freedoms are less than it appears in for when we formulate the fundamental laws of nature, and from my research area, so that is gravitational theory. So gravitation, what is Einstein's formulation, which is a Lagrangian formulation of gravity. It's a totally constrained system, but I am nowhere going to theories of gravity. I am nowhere going to quantum cosmology. So all I am doing going to do is try to see if you are thrown a Lagrangian, and can we from a simple analysis can we guess that the system is in fact constrained or not. So meaning that if you are given a systems, for example, say I take a Newtonian system with point particles designated by Qi and Qi dot is my configuration space. All right, and one can define a Lagrangian, which is a function of Qi and Qi dot. So I'm interested in showing whether the given system has any constraint, and if so, what is the condition in general for a Lagrangian to have constraints. So let me start with from the very basic that we know that Qi and Qi dot is a configuration space, and the trajectory from an initial state to final state is given by this least action principle, where I can go from 1 to n, the n particle system. So this is an abstract configuration space. Of course, it cannot be drawn for more than 3 coordinates, but let us assume that this Qi represents all the coordinates, Qi dot represents all the generalized velocities, and the correct path out of these all possible paths is given by the delta variation by extremizing this action. Now let us say what it implies. Of course, what I am going to do is derive the Euler-Lagrange equation. So del S the delta variation commutes with this integration sign, so I can take this in del L qi dot is equal to integration is equal to 0. Now I'll have del L by del qi del qi plus del L by del qi dot del qi dot 0. So I'm taking a simple system where it doesn't depend on time. So in general it can depend on time as well. By depending on time, I mean the explicit dependence. Here I assume there is no explicit dependence of the Lagrangian on the time variable. So now, applying this trick, we can write this term as a total derivative. Then we need to subtract this term So this is the total derivative term. So sorry, I forgot to mention that the integration has to be carried out between the limits initial to final. So everywhere this goes initial to final. So initial to final. Initial to final, and the least action principle says that there is no delta variation at the end point. So there is no delta variation at the end points, means that del q for each particle at initial or final points is 0. So therefore the total derivative integration with the total derivative vanishes, and this is precisely called boundary term. Okay, so we have here del q I dt. So we are only left with this term, this integration, but each del qi are independent. Therefore, the only way this integral would vanish is by the each coefficient of del qi has to vanish. So that means we have minus d by dt of del L by del Q I dot 0. This is the Euler-Lagrange equation. So I write again here the Euler-Lagrange equation. So this is del L by del Q I minus del L by del Q I dot d by dt. So same equation I am writing here. So Euler-Lagrange equation. Okay, so far so good. So we have the generalized equation of motion for each I. So this is the equation of motion. Now let us analyze this equation of motion a bit in detail. So the ultimate aim of equation of motion is to write acceleration for each I in terms of qi dot or possibly time, right, in general. So this is basically Newton's second law in a general sense. So now L is a function of qj and qj dot del L by del Q I. Here there should be a dot. So qi dot d by dt minus del L by del Q I qj dot is equal to 0. So let us split this term. So d by dt, this exact differential commutes with this delta variation. So we can take this out. D by dt of L qj dot minus del L by del Qi qj dot is 0. The next step, I operate by d by dt. So I okay, del L by del Qj plus, sorry, there is a dt over here, so it will be Qj dot plus del L by del Qj dot. So because there is a d by dt over here, it will be Qj double dot. I take this term here, so delta L by delta Qi. Okay, good. So in the next step, what I get is, let me write this first term, last term, bring this term here. So that will be del 2 L by del Qi dot del Qj dot. So there's dot here, and Qj double dot minus, is equal to del L by del Qi. So this term would go there, minus del 2 L by del Qi dot del Qj. Okay, so what you got is this. Now so Qj double dot will be del 2 L by del Qi dot del Qj dot inverse, because this would go there, del L by del Qi minus del 2 L by del Qi del Qj del Qi dot del Qij. Okay, so what we got is this. As I said, our aim is to write acceleration in terms of these are the force, or maybe the generalized force. But let us analyze this term a bit. So can rub this now. So it's clear that this Qj double dot will have unique solution only if inverse of the inverse of this matrix exists. So let us name this quantity. It is called Hessian. Or maybe I'm mistaken with my spelling here. So probably this is Hessian. So del 2 by del Qi del Qj Let us call this quantity Hessian and denoted by matrix Wij. Now it's clear that the inverse of Wij must exist. But if we notice, Wij is nothing but del by del Qi dot del L by del Qj dot. It's nothing but del L Qi and Pj. So where I am using the definition of conjugate momentum. Conjugate momentum. Okay. We want the inverse of Wij to exist, but Wij, as I said, is del Pj by del Qi dot. So inverse of Wij would be roughly so if inverse of Wij does not exist, it will mean that we cannot write Qi dot as functions of Q or P. So now imagine two spaces. One is configuration space Q and P, and one is one is configuration space that's Q and Q dot, and one is the phase space Q and P. So the inability of writing Qi dot in terms of Q and P means that the inverse function from the phase space to the configuration space, this is phase space, this is configuration space, doesn't exist. The inverse, this function does not exist means probably what is happening is one point of P is going to more than one values of more than one image in the configuration space. So that is becoming like multi-valued function that is not defined. So pictorially, perhaps it looks like this, that you cannot relate for each momentum or position in the phase space, you do not get a unique coordinate in the configuration space. This can also be seen from this matrix. So Wij, whose inverse doesn't exist, means determinant of Wij, determinant of Wij is 0. So and this is a square matrix, and we know when the determinant of a square matrix is 0, that means not all rows or columns are independent. That means the rank of the matrix R is less than the dimension of the matrix, meaning that there are less number of independent rows or columns present in the matrix than it appears to be. So this was the starting point of my talk. That apparently there seems to be more number of coordinates or more number of degrees of freedom, which are not, because all degrees of freedom are not independent, meaning that there are some constraints. That means the apparently what we see what we see the system as containing many number of degrees of freedom. There are redundancy in that, and that can be checked by this simple analysis for any general system. So it can be promoted to field theories as well, for higher rank tensors as well. So the simple analysis tells us how to check whether given a Lagrangian, can we check or not whether this system has any constraints. So essentially it means that as I said, not all Q's or P's are independent. So there are relations among Q and P. So those are, if there are M going to 1 to M relations, so where M is less than N, and it's the total number of degrees of freedom that was appearing in the Lagrangian formulation. So we have some constraints Q P is equal to 0, which are basically hypersurface in this phase space. So there could be many hypersurface geometrically, and all those constraints must be satisfied while solving the system. So I conclude here. So the takeaway message for this session was that given a Lagrangian, can we check whether the system has constraints or not. So for that we need to find a Lagrange equation. Then we need to express q double dot acceleration in terms of this Lagrangians and their derivatives, and finally check whether this Hessian is invertible or not. If Hessian is not invertible, the system has constraints. So here I end my talk. So probably in the next session I'll be talking in terms of Hamiltonian formulation and how to take care of constraints in Hamiltonian formulation. So that's all for today. Thank you very much. Thank you.